about valence electrons, okay? So valence electrons, electrons in the highest occupied energy level, S and P only, okay? So just the S block and the P block are valence electrons. Determines the chemical properties of an element. Anybody, what does the word valence mean? Does anyone know what it means? I think it probably comes from Latin or something. Anybody? Anyone know, like with curtains, they talk about a valence, like a thing at the top, right? Yes? Outside? Outside, yeah, exactly. Very good, Jared. Valence means outside. So when we talk about valence electrons, we're talking about the outside electrons, the ones furthest away from the nucleus. Okay? It turns out they're the most important ones. It turns out they equal the group number, the A series over here. And they're involved in chemical bonding. Imagine that. The electrons on the very outside of the atom are the ones that go around and mess around with other atoms, electrons' atoms. Makes sense, doesn't it? Okay? Now, let's see here. I'm going to go over it here. I think that was the last one. Okay. I'll give you guys a chance to write these down. Okay? So valence electrons are important because we need to know how many electrons are on the outside. Notice this says equals to the group number A series. So let's go over here once. I'm going to quiz you guys. This should go pretty well. This is our first objective today. Group 1A, 1A. See it? 2A. Now let's go. Nothing, 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 nothing. 3A, 4A, 5A, 6A, 7A, 8A. Notice that's the S block and the P block. 1, 2, 3, 4, 5, 6, 7, 8. Notice it says equals the group number. So this should be pretty easy. When I point at one of the elements, you tell me how many valence electrons. Like 1, 3, 5, 7. This should go really quickly.
5, 8, 3,
Louder.
4, 3, 4, 5, 6, 7, 8.
Just think if the Mr. Groves is the superintendent came around, he'd think I was teaching you guys how to count.
1, 4, 5.
Don't worry about it. We'll leave it at that. Don't worry about it. Valence electron is only for the S and P block. Okay, so someone got real clever and decided we should find a way to symbolize that. Lewis dot structures. Diagrams to show us the valence electrons. Yes?
It's okay.
Notes? Oh, that's okay. Don't worry. I'll print it out for you. Okay? Diagrams that show valence electrons of an atom using dots. Okay? Also called the electron dot structure. This isn't that clever. I mean, look at this. From now on until you die, a dot is an electron, okay? You guys got that? A dot's an electron. Check this out. Yes?
Do you have to know about Lewis?
Yeah, he's important. Gian Lewis. Lewis. We're going to learn about him again. Lewis bases. In fact, we had a gentleman who was in my class last year whose his grandfather was the top graduate student for Lewis back in the 30s and 40s. His grandfather's a professor emeritus now at Florida State University. He was an A student too. There you go, genetics. But anyways, yeah, so this guy Lewis is a pretty big name in chemistry. They came up with this idea, and at first it looks like, oh wow, you just put dots around it, but notice the dots aren't willy-nilly. Notice that, for instance, in carbon, you didn't take and put 2 dots here. Okay, look at nitrogen. Notice you didn't take like another dot here and put it here. Even beryllium, it's like, why not put 2 dots here? What would happen if you took carbon here and put a dot here? What rule would you be breaking? Hund's rule, yeah. If you don't pair up the electrons until all the spaces or open spaces are filled. We'll talk about why carbon has 4 and not 2, and 3, but we'll talk about that. But anyways, you notice as you go around, the first time you have to pair up is with nitrogen, 5. Now, once you pair up, what if I told you that nitrogen makes almost always 3 bonds? Does this start to make sense to you? 3 free electrons. And think about it. I mean, we're going to use dating as an example, but it's a perfect example. These 2 people got married. These 2 electrons got married, right? Couple. No more bonding. No more going out and making a bond. Look at these. These are single people. They can still go out and find an electron from another atom, if you know what I mean. Okay? It's that simple. Oxygen, 2 couples, 2 single people. Oh boy, this person's like all their friends are married. Okay? This is like old people. Everyone's married. Nothing's going on. That's the analogy. Okay? So notice that helium is as a duet, is stable not as an octet, but as a duet. Okay? So here's your octet. Okay? So keep that in mind. I think there's a picture of this in your textbook, so no worries. Octet rule. Atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. So if you were to go back, they all want to look like this when they're done. If they have to share, they will. Okay? Atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. And so the goal is to be isoelectronic to a noble gas. Isoelectronic to a noble gas. Okay? You guys remember that word isoelectronic? Does anyone know what that means? Isoelectronic. Do you remember that? Maribel. Electron configuration. Very close. And I think that's the next slide. I'll let you guys finish taking these notes. Okay. So I got a couple of definitions for you. Isoelectronic, ions that have the same electron configuration. Okay? So here we go. All of these have the configuration. Sorry, it's kind of small, but 1s2, 2s2, 2p6. They're all like neon. Okay? And so we've been talking about why atoms want to be like neon. When you're in middle school, they talked about the octet rule and just left it at that. Hey, 8 special. Deal with it, and you would learn that. But the reason is because they want to get back to looking like that neon where all the orbitals are filled with 2 electrons. That's stability. So they're trying to be stable, right? And everyone knows, I mean, I've been married for a long time and I've been single. I know in my life is much more organized now that I'm married than when I was single. Okay? Same thing with atoms. When there's extra electrons flying around, just crazy stuff happens. Okay? Now, another term I just want to go over really quick because I use it all the time. Halide. So everyone say that word, halide. Yeah. And these are the halogen group elements when they become ions. So group 7A or group 17, when they become F minus, Cl minus, Br minus, I minus, we don't say chlorine anymore, we say chloride. Hence the word halide, okay? And the reason this is an important term is because 99.9% of the time, these elements come to you as an ion, halide. F2, nasty gas. Chlorine, chemical warfare gas. It's actually technically not used in pools. Bromine liquid is kind of not very good, toxic. And iodine, I2, is a purple solid that basically turns into a gas, so it sublimates. It's kind of toxic as well. But everyone has heard of fluoride and chlorides. We use those all the time in our daily lives. Okay? So, monoatomic ions. A single atom with a positive or negative charge occurs when you lose valence electrons. Okay? So we're going to talk really quickly about these guys. Okay? So here they are. Notice Right now, I would like all of you to go ahead and take out your periodic table if you have it. If not, look on with someone next to you, but you should always have that. Take out your periodic table and flip it over on the back side. I can give them one here. Okay. There it is up there. So you actually have this chart. I think we did a warm-up on this. We talked about +1, +2, +3. Your textbook kind of goes +4, -4. I kind of told you we shouldn't do that. And here I noticed this left blank. This has to do with sharing electrons. We'll talk about that. And then 3 minus, 2 minus, 1 minus. And then our thing, we put 0 here. Okay? You guys have that on the back of your periodic table. However, you really should be able to do this in your head. You should know when you turn and see boron, all the elements below it are +3, 3+, okay? That type of thing. All these are 3 minuses, 2 minuses, whatnot. So sulfide, oxide, nitride. Okay? So please don't copy that chart down. You have a copy of it on you. Now, let's talk about how we name these. So here they are right here. Let's talk about naming these guys now. Jared, why is boron missing?
Yeah, boron missing.
Yeah. Basically, boron is one of those ones where it says 3+ there. The assumption is when I say 3+ that it makes ionic compounds. There's a lot of evidence that suggests that boron actually shares electrons kind of like carbon. So it's just kind of a eh. So don't worry too much about it. But good observation. Okay? Naming cations. Naming of a cation usually involves the name of an element plus the word ion. So we're really pushing the envelope here. So Na plus is called the sodium ion. I hope that's not too difficult for you guys. Sodium ion. Okay? Next. We're going to talk a little bit about alternative techniques for variable charge ions. Transition elements. Okay? Transition elements. So we hadn't kind of got to that today. Connor said since iron is a transition metal, it can have multiple charges. So now we can't just say Fe because there's +2 and +3. We have to kind of come up with a way to name them separately. We'll talk about that. It's not that difficult, okay? So, you guys got that? Okay. So now let's talk about naming those transition metal ions really quickly. In the olden days, which is like 30 years ago, so if you've run into old people that are like over 60, old chemists, they don't use this. They're kind of stubborn, so they'll call this cupric, and then they'll call this cuprous. So once you see 2+ cuprous, you think, oh, this must be ferrous. No, that's ferric. And you're like, okay, what's this? And they go, that's ferrous. And you're like, okay, well, this is tinnic. And they go, no, that's stannic, and that's stannous. And you're just like, okay, you know what? You're kind of annoying me. So we've kind of gotten away from this old-fashioned naming system. Thankfully, we got a little bit of organization, and all we've done is gone to these Roman numerals. And these Roman numerals, once you see these written out, the Roman numeral just corresponds to the charge. And they decided not to use numbers because sometimes there's too many numbers. They decided to go with these, and it just means the tin 4. So my buddy Andre was talking the other day. He's like, he'll be yellow across, like, hey, you got some copper 1. And I know that he means, do I have copper chloride, CuCl, as opposed to CuCl2, which would be copper 2. Okay, copper 2 plus would be CuCl2. So I know what he's talking about. He just wants a copper 1 source, not a copper 2 source. Otherwise, he'd say, hey, you got some cupric whatever, and it's just like, oh, which one is that again? You know, is that 1 or 2? Because that's essentially what happened. There was really no organization in this naming. It was the lowest one was the ick and then us, and it got confusing when you had like manganese, because manganese makes 6 cations, so what do you call it? You got to come up with 6 different endings. It's a lot easier to put a number, okay? So we're going to talk more about how to integrate those into naming compounds next time. But now I just want to really quickly, we don't worry too much about this. There are a few transition metals, believe it or not, that only form one oxidation state, but we won't dwell on that, okay? Let's talk about naming anions. Monoatomic anions end in I-D-E. Can't be any, so it's not chlorine, it's chloride. So we all should know this by now. It's not oxygen, it's oxide. It's not nitrogen, it's nitride, okay? And again, big difference between chlorine and chloride, okay? Deadly gas and something you eat every day. Big difference. Okay? Now, many anions are polyatomic. You need to memorize the more common ones. So again, I want you to look at the back of your periodic table. If you were in honors, the expectation is you'd kind of memorize these. But look at your periodic table right now. This will be your friend. Table 9.3 in the upper left-hand corner, you'll probably use the most of the time. When you flip this over, you'll probably look at that chart, 9.3, the most. And if you notice, it has them listed by charges, -1, -2, -3, and there's even a +1, which is ammonium. Okay? And you'll notice there are some more common ones. There's cyanide, there's hydroxide. What I'll say is memorizing the more common ones will just help you out, okay? It'll just help you out. Okay? So that will definitely be your crutch that you'll want to use on a test and things like that. Let's talk about polyatomic anions. Because in 6th period, when I did the SO4 problem with the aluminum, people got confused with the SO4 and the subscript 4 and what does that all mean. So here, I just want to show you what sulfate looks like. Okay? Sulfate looks like this. But ions that are composed of more than one atom, most are anions. They have a negative charge, okay? And that's what you see on your chart. This is sulfate, SO4. Okay? If I put a big red ball for oxygen and put here oxide, O2 minus, SO4 is 2 minus, you treat them the same way. They're an anion with a -2 charge. One just happens to sort of be a family, hanging out. They're always together. Okay? Not a big deal. Okay, SO4 2 minus, that's sulfate. Okay? So that would be one that I think you should memorize. You should just memorize it. Okay? And we'll talk later on when we do Lewis dot structures where that 2 minus comes from. And with that, the names of most polyatomic anions end in ite or ate. You have your chart. You'll see that there. I want to do this because you need to copy this down right here. Oh. Do tomorrow. So write that down. You guys got a lot of work to do tonight. Good. Bell's going to ring in just a second, so make sure you get that down or go and look at it tonight on the web. However you roll. Maribel, you still have to, Elizabeth, you still have to come up with an idea for the exam as well. We're going to take that. Okay?
It's tomorrow after school.
Fine. Okay? Because you're going to be doing tutorial. I think you signed up for tutorial to do the lab.
Yeah.
So Elizabeth, make sure you check out that thing over there before. Okay. So I'll have him hang out. I'll print him out copies. I just didn't get a chance. Yeah, I'll let him write it down. And then we have to sort that out. So just give me a second, Daniela, because I have to leave this up.
Mr. Jessup,
Yep.
for the purpose of the lab, do we
Yep.
just do that on a separate piece of
Yep,
paper?
on a separate sheet of paper, just type out your purpose, turn it in, okay? So I think pull up your early quizzes. Look for those. It's kind of right after, and then the homework, like from the first homework packet, I think.
Thank you, Mr. Jesse.
Okay, see ya, Jared. Okay. So you got it, Leo? You got it?
Yeah.
That's your first homework packet?
Yeah. Oh, yeah. And then, do you know like which
The first two, like the element quiz and the first one.
like the very
Yeah. I know.
I have to like look for if you want to go, you can use it. I can't have to wait because I don't know how long it's going to take. Is it this one?
Yeah. Okay. So Leo, I'm gonna give you a copy of this, Leo. I gotta go through here real quick, okay?
Mr. Justin, could I take my test Wednesday during lunch?
Yeah.
Okay.
Okay. I'm gonna print this out for you, okay?
Page 2, the 81,
81, 42 through 46.
42, 46.
Okay. I'm gonna print a copy of you out though for you, okay? So wait, Leo.
Yes, I did it.
Yeah, but I'm gonna print the whole thing out for you. Okay, so